Hi everyone and welcome. In this video, I'm going to walk you through HealthyByte, a simple AI-powered application that acts as your personal cooking assistant. But it's not just about recipes. This app is a hands-on demonstration of tool calling with Genkit. We will start with a very quick overview of what Genkit is and what tool calling enables. Then I'll do a short demo of the application, and then I'll show you a high-level overview of the app's flow and guide you through the actual code, both back-end and front-end, in detail, so you can see exactly how it all comes together step by step. If you would like to dive deeper or try it out yourself, the full source code is available in the GitHub repo. You'll find the link in the description below. And finally, one more assistant will be joining us today. Gemini's text-to-speech feature. Since English isn't my first language, as you might hear, I've decided to let Gemini help out with some of the voiceover commentary in this video. Let's get started.
Hello. As Renaud mentioned, I'm his assistant, and I'll be taking care of the voiceover for the rest of this video. Let's take a quick look at what's coming up. Here are the main sections. Section 1, App Demo. Section 2, Genkit in a nutshell. Section 3, Genkit tool calling. Section 4, App Flow. Sections 2, 3, and 4 will be quick overviews, just enough to give you the right context before we dive into the code. The heart of the video is Section 5, Code Review. That's where we'll really dig into the code line by line so you can see exactly how everything works. All right, let's get started with a quick demo of the app in action. Here is the single screen of HealthyByte, our demo application. I enter some ingredients into the input field, then click the Suggest Recipes button. The app calls the Gemini 2.5 Flash LLM through Genkit. After running the Genkit flow, including the tool calls, the backend returns the LLM's response. First, we get 3 recipe suggestions based on the ingredients provided. What's important to note is that each recipe comes with detailed nutritional information, retrieved via the tool calling the Nutrition API, which we'll explain in the next section. Finally, at the bottom of the page, we have the recommendation from our chef assistant. Based on the nutrition facts, the ingredients, and the cooking method, it determines which recipe is the healthiest choice.
Let's take a very quick look at Genkit and some of its key features. Genkit is an open-source framework for building full-stack AI-powered applications. It offers a unified interface for integrating AI models from many model providers. It provides dedicated SDKs for Node.js, which is a stable version in general availability, Go, which is currently in beta, and Python, which is currently in alpha. Deploy AI logic to any environment that supports your language, such as Cloud Functions, Cloud Run, or third-party platforms with or without Google services. Use Genkit monitoring to gain visibility into how your AI features perform in production. For more details, please see the official documentation at genkit.dev.
Let's now look at Genkit tool calling. Among many other features, Genkit provides a single interface for tool calling with models that support it. Tool calling in AI and LLM-based application development allows LLMs to make requests back to the application that called it or to interact with external tools or APIs. Tool calling use cases generally fall into a few key categories: providing an LLM with access to external or real-time information not available during its training, adding determinism to an otherwise probabilistic LLM workflow, triggering real-world actions based on decisions or outputs generated by the LLM.
All right, last slide before we dive into the code. Let's walk through the app's flow as illustrated in this diagram. First, our web front-end calls an HTTPS callable cloud function exposed via Genkit, passing in the list of ingredients. That triggers the execution of a Genkit flow, which uses the AI plugin to call the Gemini LLM. As part of the prompt execution, the LLM makes a tool call via Genkit. This tool interacts with the Nutritional Ninja API to retrieve nutritional data. The tool is called 3 times, once for each of the 3 recipes generated by the LLM. The LLM then uses the results of those tool calls to enrich its response and sends the final result back to Genkit, which in turn returns it to the front end. It's worth noting that while we're using a web app for this demo, the exact same flow would work with a native mobile app, whether it's built in Android, iOS, or Flutter. Callable cloud functions exposed via Genkit can be invoked just as easily from mobile as from the web. All right, time to dig into the code. Let's first start the most important part, the Genkit backend code. First, let's look at the dependencies we're importing at the top of the file. This is the core Genkit library. It provides the foundational functions like Genkit for initialization and AI.generate for interacting with models. This imports the Zod library. In Genkit, Zod is used to define schemas for our inputs and outputs. This is powerful because it ensures type safety and predictable data structures when dealing with LLMs, which can otherwise be unpredictable. It also defines a clear interface between back-end developers and front-end developers. This is the official Google AI plugin for Genkit. It allows our application to connect to and use Google's generative models like Gemini. This is a helper function from the Firebase functions library. It acts as a bridge, allowing us to easily expose a Genkit flow as a Firebase callable function that can be very easily called from your front end using the Firebase client SDKs for JavaScript, Android, iOS, or Flutter. Axios is a standard promise-based HTTP client that we'll use to make a request to an external, third-party API for nutritional data. Finally, define secret is a security feature from Firebase functions. It allows us to declare that our function needs access to certain secret values like API keys, which are managed securely by Google Cloud's Secret Manager. After all these imports, we declare the secrets our application will use, the API key for Google's Gen AI services, and another key for the API Ninjas service. The Genkit function is the heart of our setup. We pass it a configuration object where plugins is an array where we register all the plugins we want to use. Here, we're activating the Google AI plugin. The model property sets the default model for our application, in this case, Gemini 2.5 Flash. By setting a default, we don't have to specify the model every time we call the generate function, which simplifies our code.
Now let's look at the main business logic, which is encapsulated in a Genkit flow. A flow is a sequence of steps, which can include model calls, tool executions, and other logic. We start by wrapping everything in on-call Genkit. This makes our entire flow a single callable endpoint. We pass the secrets we defined earlier to this wrapper, which makes them available as environment variables within the function's runtime. Inside, we use AI.defineFlow to create the flow itself. It takes 2 arguments, a configuration object and the async function that implements the logic. Let's firstly detail the configuration object. We give our flow a name, recipes suggestion flow. This is useful for logging and debugging. Using Zod, we define the expected input structure. This flow expects an object with a single key, ingredients, which must be an array of strings. Then we define the exact JSON structure that our flow must return. It must be an object containing a recipes array and a healthiest recommendation string. If the code tries to return something else, Genkit will throw an error, preventing malformed data from being sent to the client. Now let's look at the flow implementation. The async function receives the input that has already been validated against the input schema.
The core of the logic is the awaitai.generate call. This is where we interact with the Gemini model. Let's detail the object passed to the generate method. In config, we set the temperature to 0. A low temperature makes the model's output more predictable and less creative, which is what we want when we're asking for structured data and factual analysis. Tools is a critical parameter for our application, which call implements tool calling. We pass an array containing our custom nutrition facts tool. This tells the model that it has this tool at its disposal and can choose to use it if the prompt requires it. Finally, we have the prompt. We tell the model its persona, a professional chef, its task, generate 3 recipes, and the exact JSON format for the output. Crucially, we instruct it how and when to use the nutrition facts tool to get the nutritional information it needs to complete its task. Finally, the flow returns LLM response.output, which contains the final JSON object generated by the model after it has run the prompt.
Okay, now we're going to focus on the nutrition facts tool, which enables our AI agent to interact with the outside world. In this case, an external nutrition API. We create the tool using AI.define tool, and we'll now go through each parameter passed to this method in detail. Name is the unique identifier for the tool. The LLM will use this name when it decides to call it. Description is arguably the most important part. The LLM reads this description to understand what the tool does, what its capabilities are, and when it should be used. A clear, detailed description is key to reliable tool usage. Input schema defines the data the model must provide when calling this tool. Here it must provide an object with an ingredients list string. The .describe method adds extra context for the model. Finally, output schema defines the data type the tool's implementation function will return. In this case, it's a simple string. The implementation is relatively simple. The async function is the code that runs when the tool is called. It makes an HTTP GET request to the API Ninja's nutrition endpoint using Axios. Now we arrive at this line, const nutrition information schema.safeparse.response.data. Before we continue, let's look at how that schema is defined. This ZOD schema defines the exact structure we expect to receive from the external API Ninja service. It's z.array, meaning we expect the API to return a JSON array. Each element in the array must be a z.object that conforms to the specified shape. We define every property we care about, like name, calories, fat totals.g, and sugar.g, along with their expected JavaScript types, string or number. This schema acts as a contract between our code and the external API. By validating the API's response against this schema, we protect our application from unexpected changes in the API's data format and prevent bad data from being processed further. Back in the tool, nutrition information schema.safeparse.response.data attempts to validate the data. We use safeparse because it doesn't throw an error on failure. Instead, it returns an object with a success property. We can then check if not parse.success to handle validation errors gracefully. The final steps in the tool are as follows. 1. If validation succeeds, parse.data contains the type-safe data. We use reduce to sum up the key nutritional values from all the ingredients into a single total object, but note that we don't include all properties from the raw response, because the free version of the nutrition API doesn't return complete data. For example, fields like calories may return a string like only available for premium subscribers, which we intentionally exclude from the aggregation. Finally, the tool returns a formatted string summarizing these totals, which fulfills the contract of its output schema. This string is what gets passed back to the LLM. The LLM then uses this information to populate the nutrition information field in the recipe objects it's generating and to determine which of the 3 recipes is the healthiest. And that's the complete loop.
We will now inspect our front end, which calls the recipes suggestion flow. The front end is a very simple HTML and JavaScript page. It uses Bootstrap for layout and styling, and it connects to our back-end logic through Firebase Callable Cloud functions, which are powered by Genkit. In a real-world production app, you typically use a framework like Angular, Vue.js, or React to handle the front-end logic and templating more robustly. But for demo purposes, this plain HTML and vanilla JavaScript setup keeps things lightweight and easy to follow. The interface is minimal. Users type a list of ingredients in a single input field and click the Suggest Recipes button. This triggers a call to the back-end cloud function, which runs the Genkit flow using Gemini 2.5 Flash to generate healthy recipe suggestions based on those ingredients, just as we saw earlier when analyzing the back-end code. Once we get the result back from the cloud function, we simply update the DOM using basic JavaScript to display the recipes and the LLM's recommendation. Let's zoom in on two key parts of this front-end code. First, Firebase SDK import and initialization. This part imports only the Firebase modules we need, Firebase app and Firebase functions. We then initialize Firebase with our project config. Note that this is a public client-side config, so it's fine to include in the browser. And we get a reference to the Cloud Functions service. From here, we can call any callable cloud function we've deployed, just like calling a normal async function in JavaScript. Second, calling the Genkit flow via Firebase Callable Cloud function. This is where the real action happens. We call the recipe suggestion Genkit flow through Firebase functions using HTTPS Callable. We pass a simple payload, an array of ingredient strings, and Firebase handles the serialization, network request, and parsing of the response. We await the result and use it directly to update the DOM with the returned recipes and the nutritional info.
So, in short, this front end may be simple, but it's fully connected to powerful Genkit flows in the cloud, with minimal code. What's really important to note is that this exact same approach works just as easily on iOS, Android, or Flutter. As shown in this Firebase documentation page, Firebase provides native client SDKs for all major platforms, and calling a callable cloud function is always just a few lines of code. No need to write your own HTTP client or custom backend logic.
Thanks for watching. Hope this helps you get started with Genkit and tool calling.